Now, after 65 years of effort to get unified theories, the situation is perhaps reversed. Now, the idea is that apart from the success of unification of weak interactions, still we have the same effort as Albert Einstein to try to unify gravitation and all the interactions. And now the idea is that you have to change the geometry. There is the formal part becomes important. Is that right or not? I would like to hear your opinion on that.
Well, I don't think it's really possible to make any theoretical prediction about how a new step in physics will happen. After all, quantum mechanics started in a way that nobody would have guessed, by making a theoretical fit, not even a theoretical fit, by making an analytical fit to experimental data on black body radiation. Quantum mechanics started. That was a pretty weird way for a theory to start. The string theory started with a clever formula written down by Veneziano in an effort to satisfy not so well motivated phenomenological ideas about strong interaction scattering. That was a way for a theory to start which was as strange as the way quantum mechanics started. And the way Einstein happened to have invented a theory in a particularly striking triumph of reason and intuition, but most other physical theories have had more complicated histories. And it's hard to make theories about them.
You can't generalize at all of how invention will come. Anybody who makes statements like that is going by his own experience. And I think these statements must be modified according to each situation. What would you say, Dennis?
Well, it still seems to me it's a question of whether you start with a mathematical scheme and then look for a physical interpretation, or start with a physical principle which you guess to be correct, and then on the one hand try and prove it experimentally to be true, and on the other hand codify it into a mathematical form. I must admit I've always been so admiring Einstein's procedure in general relativity of starting with a very simple physical remark based on the Galileo discovery that bodies of different mass fall at the same rate in the gravitational field of the Earth. He made a simple physical hypothesis why that should be true, and that forced all the complications of non-Euclidean geometry and so on to put the physical idea into a proper form. But if you'd started by saying, let me think of a mathematical scheme that might lead to gravity, let's try non-Euclidean geometry, that would have been, to me, a very strange way of proceeding.
Einstein had all the field theoretic theories of gravity with spin 0 and spin 1, of course, wrong. Before he started, he knew all that. Then he had all the intuition of the non-Riemannian geometry from the work of Gauss and Riemann themselves. So if Einstein had not started and had not lived even, I'm pretty certain that 2 or 3 or 4 years later, somebody may have hit upon the same things. Hilbert nearly did.
Well, only stimulus from Einstein. I agree with you, except that I think it would have taken
Longer, yes.
You see, Riemann almost did it. Riemann had the conception that gravity was based on curved space-time, but what he lacked, Riemann had the conception that gravity was based on curved space. He didn't conceive of curved space-time because special relativity hadn't happened yet, so time and space hadn't been unified. But if Riemann had lived after special relativity, he might well have
lived. Sure. Gauss made even the experiments, you remember. So I don't think it's such a cut and dried case ever.
Well,
Let me give you one more example, if I may.
Please.
About invention and so on. Dirac, whom we were celebrating today by giving Ed Witten the first Dirac medal, was a great advocate, you may remember, of pure thought and handsome, beautiful theories and so on and so on. Mathematical beauty. If there is a mathematical beauty in the theory, it must be true. Even though experiment didn't show it. Now, it so happens that supergravity or supersymmetry is a very beautiful theory. There's no question about it. I had the privilege of lecturing on this subject in 1974 when Dirac was in the audience at the Miami conference. Dirac, of course, as usual, kept quiet, didn't say a thing. And I pressed its beauty, its renormalizabilities, and all the great points about in favor of this theory. He didn't say anything, so after the lecture I went to him and I said, Professor Dirac, don't you think this satisfies all your actions of very, very beautiful theories? And wouldn't you like to believe that this is the truth? And to my amazement, Dirac, of all people, said to me, if this theory was true, it would have been discovered long ago. The truth of supersymmetry would have been discovered long ago.
Experimentally, you meant?
Experimentally. Now, there was the true physicist like us, humble people speaking, not the Dirac which we had learned from. So I would not like to be too dogmatic about any of these axioms which Paolo has read to us.
If it turns out that string theory is right, it will extend the historical range of how theories have been discovered in a very interesting way.
Very interesting way.
Because its discovery is as peculiar as the history of any really major discovery.
That's right.
And anybody's scheme for how major discoveries can happen will have to be very flexible if a pre-existing scheme agrees with this one. In fact, if there is a pre-existing framework, if someone has a theory of discoveries, pre-existing theory written before string theory, which is flexible enough that it can accommodate this one, then I suspect it has little predictive power.
But could I defend my position a little bit? I see, sitting at the side, as it were, various clever people inventing new mathematical schemes. There's the scheme we've heard from Ed Witten just now, so beautifully expounded in his lectures. We've got Roger Penrose with twistors.
Yes.
We have other people saying, let us start with not a differentiable manifold, but some other more primitive topological structure for space-time, and so on. The difficulty is, how do you decide which of these mathematical schemes is on the right lines if you've no guidance from a physical principle that I was asking for before? Each of these schemes separately is beautiful, I would say. But there's no guidance as to which is likely to be right.
Let's take the string now. I do not know whether Ed would agree with me or not. I do not know of any reasons apart from duality, but there's no test of duality really, is there? Very, very feeble. So string theory is a good example of your type of worry, where mathematics is driving, or rather the formalism is driving the theory. But I think the uniqueness of this theory is a very appealing thing. Wouldn't you say so, Ed?
Yes.
I think that the mere fact that it's a unique, well, there are millions of ways of getting to the strings, as we heard from Ed. But apart from that, the fact that in the end there is a string and so on, which is going to replace space and time in some special way, is, I think, significant and giving you a unique theory. What I wanted to ask you was, in the end you were getting to a phi cube-like theory.
Yes.
Now, this has never happened before, that a light cone gauge thing, which light cone gauge also gives phi cube as the unique theory. It's never happened before that the light cone gauge has given you the same type of theory, formally, as a non-light cone gauge thing. What I mean is, for example, so gravity in light cone gauge.
Yes.
It's horrible. It's horrible.
Oh.
Wouldn't you say so?
Yes. Well, this also is horrible in light cone gauge by comparison. These first, actually, the light cone gauge for the open string has a quartic term as well, which Frangebar was asking about. But the light cone gauge for the open string or closed string involves much nastier formulas.
Well, they are phi cube or phi 4 with some derivatives and so on.
Yes, but non-localities and
Non-localities, I agree with you.
When you say
you are hoping that when we will go to a supersymmetric case, those non-localities will disappear. Is that the point?
I'm not committed to using light cone gauge for anything.
No, my fear was that in the end, after the dust is settled, you may come back to the same sort of structures as the light cone gauge is already giving. And in that case, we shall not have scored a greater triumph this time than we have in the past.
Well, that's right. Well, the way I would put it is that I think it's more satisfying to have a gauge invariant framework from which you can derive the Veneziana model. But to be really true, it would have to lead to other things that would simplify it and explain the logical structure.
Yes.
Right now, it's nice to have a framework where you can only have one Lagrangian, but it would be even nicer to have some reason that this particular algebra would inevitably appear as the answer to some question. And that's the kind of thing that has to happen if what I was lecturing about is on the right track.
And things is certainly true, but
yeah.
I don't know.
Super well, the convergence, I mean, the ultraviolet disappearance of more than the Veneziano. This was the real origin, no? Well, the reason why it becomes so important.
Yes, this is
the hope.
Yes. Well,
But-
Ed thinks it's certainly true, but
Yes.
I don't know.
And then it would not imply some revision of the conception of space-time, of
Well,
drastic
that's already
conception.
come. That's
Yeah.
already come, as you heard today.
Yeah,
For
and
example.
so yes. And
Uh,
so it is a drastic,
I
probably a
believe-
drastic revision of our
Oh,
concept of geometry.
I believe that, like the Bohr atom, in its day, string theory has within it the seeds of a real revolution in the way we understand physics.
Yeah,
String theory we understand in a very primitive way,
yeah.
but I think locked in it, there are some amazing things that have to be unlocked.
The relationship of quantum theory and general covariance and so on. I don't know if you, my good, I shouldn't call him a pupil, my colleague, Professor Isham at Imperial College, he once said to me that he joined quantum gravity bandwagon in order to get out of space-time, which he loved more, equivalence and diffeomorphisms and so on, quantum theory. And with strings, the opposite seemed to be happening.
Mhm.
That's just the remark which you were making. Is that right?
Well, I'm just not convinced that we know which of the ingredients that we now know from string theory will prove to be more fundamental.
But didn't you say that quantum theory was not going to come out of it?
Oh.
That was the question.
I said that indeed string theory might explain quantum mechanics in the sense that string theory might be, for the first time, a theory which was more natural as a quantum theory. After all, if you take it at face value, it was first discovered as a quantum theory. The first things calculated were scattering amplitudes.
No, but where would you say the quantum quantization principle is coming in?
What?
Where do you think fundamentally, basically?
Oh, I don't know.
When you speak of the structure of space and time or some
Yes.
revolution thereof, would you not expect that you would get a new structure in which somehow quantization principle superposition
Is
and so on
automatic?
Are
is
inbuilt.
automatic?
Well, that would be better. It would be far better if string theory does explain quantum mechanics.
Yes.
But in the spirit of trying to take some steps, since you can't do everything all at once, I tried to take the conservative hypothesis of assuming we might not explain quantum mechanics, but only a fundamental
Uh-huh.
generalization of
Yes.
the known symmetries.
Yes. I'm being those people who are looking within quantum gravity, the origin of quantum theory from gravity theory
Yes.
have been defeated.
Mhm.
Well, I think that they should start working on string theory because it really has a potential to do what they've been dreaming of. You see, I made such a point of saying that I wasn't going to assume that string theory would explain quantum mechanics, just to plant in people's mind the fact that there's a question that maybe I am being too conservative.
Yes.
Yes, I took it that way. But quantum
Right.
mechanics is so weird. I mean, although it's an old theory, its weirdness is coming out more and more into the open in recent years with various discussions. So it's not at all clear that just saying matter is made of strings is going to explain this weirdness, which seems
No,
on a different level of structure somehow.
By which space-time is different than we thought. And by which, I mean, one could go back perhaps to Cartan. He said this the same thing, I mean, in 37, that Euclidean geometry is a very complicated geometry, while the geometry of zero vector is the more elementary one. Now, there is a lot of zero vectors in these minimal surfaces. I mean, the zero vectors, this was known 150 years ago, that zero vectors generate by Weierstrass minimal surfaces. So maybe that is also, that the Euclidean geometry is not the most elementary one.
You say that Cartan discovered the exceptional groups?
I think.
Did I
I said
understand?
it, and I hope I didn't get it wrong.
No, I think it's.
Is that true? They
I
were not
think it's-
discovered by Mr. Lee, Sophus Lee.
Maybe the infinitesimal, the algebras, but the groups were first done.
No. E8 as a group was only done much later. Neither Cartan nor Lee proved that there was an E8 group.
Oh.
If I'm not mistaken, Cartan discovered the E8 Lee algebra, which had been unknown to Lee.
Which is unknown to Lee.
Yes, Lee what Lee did with Lee algebras, I don't know, but you could do it. Obviously, he must have maybe introduced the general concept of Lie algebras, although some special cases have been done before
Yeah.
and proved some basic theorems about them, but he didn't classify them. I'm pretty certain. You see, it's difficult, even if you have a Lie algebra, to determine if there is a corresponding group. Not every Lie algebra can be exponentiated to give a Lie group. And you can prove that, let's say, for the SON Lie algebra, there is an SON group by actually describing it as orthogonal motions of space. But to prove that there is an E8 group was apparently difficult.
Did you discuss the what we expect experimentally today from the string theories?
I actually think that one of the few predictions that have been made, which haven't been made in the context of other theories, is the existence of fractional electric charges that aren't confined.
Is that a definite prediction which will not be changed?
Well, I think it has a higher probability of staying than anything else.
Because you stated it for the first time in a rather small paper.
No.
No?
I wrote a long paper with my student Wen.
Oh,
I wrote a survey of the theory in which I stated it rather briefly, perhaps.
I see. But you think that this is, there are many elements here.
Yes.
Secondly is their confinement. Now, are you sure that they will, someday you will not want to confine them again?
I don't think there's any reason they would. They don't have any real quantum numbers except electricity or other abelian quantum numbers. You see, the burden of proof is to show that there aren't fractional charges. Now, in 4 dimensions, we prove there aren't fractional charges in standard unification, because unification or symmetry breaking we do with Higgs expectation values, which we can turn off continuously. And turning them off, the representations must go over to representations of the unified group, and the unified group doesn't allow fractional charges. But if we're going to work in string theory, the symmetry breaking has to be something that can't be smoothly turned off. And that means that there's no reason there shouldn't be fractional charges. And I believe that it should be a generical property of models of that kind, even if many ingredients we now think we understand actually are wrong.
This fractional charge is not one. How did you determine that 1/5?
I really, well, the states that have 1/5 electric charge are states where a closed string wraps around a non-contractible loop.
I see.
And if you just calculate the electric charge of such a state, you get 1/5, or a multiple of 1/5.
I see. So that's quite spectacular.
Well, the discovery would be, but of course, since the particles have Planckian masses,
Yes.
they wouldn't sit at the center of the Earth. The Earth's gravity would attract them to the center. Sorry, they wouldn't sit on the Earth's surface. Gravity would pull them out of. Such a particle with its feeble electric charge and its heavy mass wouldn't be electrically bound in atoms. Gravity of the Earth would pull it right out.
Well, I was going to ask you, Ed, actually, following on Abdus's question, looking for consequences of
Yes?
this new scheme. Would there be either astronomical or cosmological consequences specific to the new scheme?
10 to the minus 5 grams.
Maybe the missing mass.
Well, you know, a question like that is difficult to answer because the interaction of particle physics and cosmology is frequently quite nonlinear and unpredictable.
What about this lens effect and those things that you talked about in one of your papers?
Well, okay, so
Strings in the cosmic sense.
yeah. Okay, you can ask the question of whether there will be some kind of the superstring itself is some could exist as a microscopic string. We usually imagine it as a microscopic string, but if it's a closed string that can't break, you could stretch it across the horizon. But it's actually so fabulously heavy that that kind of string couldn't really exist in our world today. Also, it turns out that they are the boundary of axion domain walls, which would have presumably caused them to disappear. But we can ask whether string theory would give rise to somewhat lighter cosmic strings, like have been discussed by Kibble and Blanken and others. And, well, since I've always been a fan of those cosmic strings, I hope that the answer is yes. But you can easily describe many plausible scenarios by which they might arise, but you certainly couldn't say there's a prediction.
Charges.
Yes.
You don't think there's a QCD-like argument to be made about confining them?
No, because they don't carry non-abelian quantum numbers.
They don't.
Well, to differently put, any non-abelian quantum numbers they could carry can be screened by ordinary
Yes.
particles.
Yes.
The only unusual thing they carry is electric charge 1/5. By adding to them standard quarks and things,
Yes.
you can make a state which is neutral under all non-abelian quantum numbers and has electric charge 1/5. So if electricity isn't confining, they won't be confined.
Oh, I see. I see. So they are a definite prediction, you think? Which will
Not
not be
with
altered.
probability 100, but I think it's such a natural consequence of a theory that is only unified in higher dimensions that there's an excellent chance it will survive. I wouldn't say that. Like, if you ask me, do I think it's an E6 or an SO10 model or a
No,
monofold
that
messenger
I
dynamic?
think is, as you said yesterday, is really still to be fitted.
Right.
Yeah, fixed.
Or
and
if you
so on.
ask, are there extra U1s or how many generations?
How do you think you would eventually get this low mass scales into the picture? Some sort of exponentiation of something or the other?
I hope it's an exponentiation of something. Well, of course, it's not clear why the fine structure constant is small. Microscopically, there's no dimensionless parameter,
Yes.
but somehow a small parameter has to come out of it anyway. And to get a big number or a very small one by exponentiating it, you already have to have a moderately small number, and even that's slightly mysterious. Last summer, I was reading the fascinating book by André Weil on the history of number theory,
Oh yes.
from Hammurabi to Legendre.
Oh yes.
This way.
It's quite interesting.
Yes.
But he discusses Fermat's adventures with some simple Diophantine equation,
Yes.
where Fermat found that the lowest integer-valued solution was something times 10 to the 15
Oh.
of some innocent-looking equation.
Oh, I see. Something.
So,
Those things may play a role.
well, I don't know if I'm really suggesting that the world is based on some strange solution of a Diophantine equation, but it's really interesting that he had a problem that was defined by numbers of order unity, but the solution was some gigantic number.
Yes. Yes.
Going back to the cosmic strings, the very long ones that might occur in astronomy, you were telling me the other day that they may have seen some of these strings coming out from the centre of the galaxy. Do you take that seriously?
Seen that, really.
Yes, that's...
Well, I wish I were a radio astronomer and could make a more independent judgment. The majority of astrophysicists that I've asked about it express a skepticism, or at least caution, similar to yours. And I'm not in a position to have an independent judgment. I hope it's true, because I think it would be a great thing for both astrophysics and particle physics if cosmic strings were discovered. In fact, for particle physics, it would be one of the fundamental measurements. You'd measure at least the mass of the string if you saw it at all. I believe you'd find ways of measuring its mass. And that would be a fundamental measurement of a new scale of symmetry breaking, probably way beyond what's accessible to accelerators. So,
What would a measurement imply? What would one have to do to get a measurement?
well, it depends on how heavy it is. Vilenkin pointed out that if it's heavy enough, you would actually see it as a gravitational lens.
But the original idea was that these were the seeds of galaxies, that
No, the
galaxies
seeds of
form that way.
galaxies are finished.
Yes, but now these are
Galaxies
strings you
are
actually see as a string in the sky, you see. That's the idea.
Okay, originally, Vilenkin and others investigated ways of observing strings by their gravitational interactions.
Mhm.
But there's another possibility for observing strings, because under certain conditions, one of these cosmic strings is an electrical conductor, in fact a superconductor.
Mhm.
And as a superconductor moves through the conducting plasma of interstellar or intergalactic space, well, it's superconducting moving in a magnetic field will push the magnetic field lines upstream. And to do that, it has to start carrying the current. So pretty soon you've got a gigantic current wreaking havoc with the magnetic fields and creating all kinds of storms and who knows what. In fact, I think the plasma physics involved would look rather complicated. Complicated enough that I've certainly never attempted to understand it myself. But the New York Times, on the first page of the science section, published a very amusing picture a couple weeks ago of the galactic center. It's a radio picture of the galactic center with some threads coming out.
Okay.
The threads are 100 parsecs long and 1 parsec across. And George Fields, the astrophysicist, is quoted as making the speculation that these could be cosmic strings, by which I presume he meant superconducting cosmic strings, which
How were these maps made in the first place?
I don't know the details, but generally speaking, it's a radio picture of the galactic center made with, I think, the VLA, a very long baseline interferometer. It has much higher resolution than previously, which you need because the thread which is being detected has a width of order 1 parsec at a distance of 10 to the 4 parsecs.
10 to the 4.
I think it's
It's a-
marvellous.
it's a
As
thread.
I heard it first just yesterday. My immediate reaction was you could find a more conventional explanation, which I'm sure is what your astrophysicist friend said, but who knows? Who knows?
Oh, the 1 parsec would arise because no matter how thin it is, as a superconducting wire travels through the plasma,
Yeah.
it produces tremendous disturbances, which can easily extend out to a parsec.
I see. So it's
Yeah.
Terrible magnetic storms and cosmic ray showers. Really, I think there's a good chance you'd at least measure its mass. Regrettably, Vilenkin showed, I guess, that it wouldn't really be a source, that a perfectly straight thing wouldn't really be a source of Newtonian gravity.
But you mean from the bending of light coming past the string?
If it's heavy
with
enough,
the lens effect.
yeah, if it's heavy enough, then once you see it in the sky, you definitely can look for things like double images of foreground objects.
Uh-huh.
Although actually, this is thick enough that you'd have to do your observing at some wavelength to which the thing is transparent.
Do you mean Cygnus X3-like objects as we understood them before the suggestions, the muonic showers and so on? Because I think the data there is not accepted as correct.
The
So.
muonic showers?
Yes.
Why not?
Well, no, I
Two
just...
labs out of 4 which could have detected it, and that's good enough
Well,
statistics, isn't it?
I'm being conservative again, since analysis shows it would require quite new physics. I mean, particles coming from Cygnus X3 of a new type to explain the positive data.
Not a really new type. I mean,
That's what I'm...
no, I don't think so.
I call that new physics.
Oh, I see. No, but
so
this,
therefore, if half the observers don't see any effect, you see, then it seems to me one should be conservative about it. But to predict how many objects like Cygnus X3 from an astronomer's point of view should be present, say, in our own galaxy is too difficult. Till you understand
the Cygnus X3 in our galaxy? I thought
Yes.
it's outside.
No,
Are you sure?
it's in our galaxy.
Is it?
Because the magnetic field, the high magnetic field, rotating at such velocity gives a velocity higher than light at a certain distance, which produces this effect according to him. So he said it is one of the effects that he had foreseen for neutron stars, naturally.
How about how long they last for?
Yeah, that's another question.
I've heard it said that Cygnus X3 could be producing most of the cosmic rays in the galaxy at high energy.
To the 5 TeV or whatever it is being produced. What I'm really asking is, could we have some brother of Cygnus X3 which would produce 10 to the 16 TeV?
Well, it would be nice, wouldn't it? I don't know. I don't know.
There's nothing to stop it.
Incidentally, superconducting cosmic strings, depending on the particle physics,
Yeah.
can produce particles of incredibly high energy. Because as it travels through a magnetic field, in displacing the field lines, it has to pick up bigger and bigger currents, which are carried by more and more energetic particles. And eventually, in too strong a field, with too high a current, any superconducting wire goes normal and will expel all those particles in some dreadful cosmic ray burst.
I see.
Well, the
Dennis?
conventional explanation is that it's in supernova explosions, at least up to some energy, not perhaps the very highest energies that are detected. This would occur just within our galaxy. But the very highest energies may be made in external, more powerful galaxies where explosions perhaps occur at the center of the system, and those cosmic rays come to us. Well, there's no definitive proof that this very favored view is correct. Energetically, it's reasonable. We know how much energy supernovae put out in our galaxy, and if, say, a few % of that went into cosmic rays, then energetically that's all right. But that's not proved.
Picture of cosmic rays?
Yes, well, it could do, certainly at high energies, or even maybe at lower energies. It's often very difficult to demonstrate that a theory that on energetic grounds is adequate enough to do it is actually the dominant source. Because if it happened to be only producing a few % of what we see, then of course most of it is made by some other mechanism. So we don't. But of course they do. You see, as they propagate in the galaxy, the galactic magnetic field stirs them all up, so that you can't just tell from direction of arrival where they came from. That's one of the fundamental difficulties, of course.
If it were true that cosmic rays, at least in some energy range, come mostly from Cygnus X3, it would be a dramatic illustration of the need for experimental science, because it would have been hard to guess, for theorists to guess that in some energy range, cosmic rays were mostly coming from some weird object.
Oh, of course.
Oh, yeah.
Absolutely. My
Well, it
goodness.
really is a fascinating study, how one can spend ages hitting one's head against something which is experimentally totally irrelevant. Take SU3. I don't know how much influence SU3, the old-fashioned flavor SU3 had on your thinking, but for us it was the end-all and be-all. And by God, it's such a lousy group to deal with, such a lousy group to make into fundamental sense that we at least I heaved a sigh of relief when it went away and became SU4 or SU2 cross SU2 cross SU2 or whatever it is.
Or what became explained as a consequence of quark masses,
Quark
which we should think about.
masses, yes. So really, I mean, experiment is such a balm sometimes to theoretical prejudice that it's a fascinating study if somebody should.
It certainly is sobering to see, also very frequently, how one can be very close to the truth of something, but by making a slight error, well, the Cygnus, because of some missing ingredient, which for cosmic rays could have been Cygnus X3, or
Yes.
some little fact that you just should know in order to investigate this problem, you could reach completely
All the
wrong
theories
conclusions.
of
But he didn't know which the sources were. He just
Well,
said this is a way of accelerating the particles in
because-
cosmic conditions.
Yes.
Is it still considered a major mechanism?
Oh, I think so, yes. Yes. Although it doesn't work quite as effectively as he thought in the interstellar medium, but it may work in the shells of supernovae, for instance. But of course, astronomers suffer from the fact that they can't do experiments in a systematic way. They have to wait for messages from outside.
well, I would like to say Fermi, but
Well, he made a theory, I mean, about clashes with the magnetic field.
yes. Before SU3, before that was SU3, which was a horrible group. I mean, if you had, well, you didn't live through that period, you were lucky. But we used to beat our heads against the wall, trying to make a fundamental theory of that SU3.
You can build a machine in the lab systematically to study
Yes, you
problems
can't
you
even
want.
do that. Yes.
as long as the energy is within
Yes.
within bounds.
But it's a little chaotic how long you have to wait before those machines
That's
find
right,
something.
that's right, that's
But
right.
after
yeah.
all,
I'm one of those astronomers who prefers to control fantasy with observation.
Of various sorts, which will change astronomy completely out of recognition soon. What's your time scales of changes, big changes?
Something that, well, like Space Telescope,
Yes.
which we hope will go up soon, that will extend our powers of observing stars and galaxies tremendously. But it's the same kind of astronomy as before, just with somewhat more powerful instruments. But we can't actually go out to Cygnus X3 and look at it and see what it's made of, for instance. That's what we'd like to do.
Do you think there's any even imaginable plan for an interstellar space probe? Not manned, of course, instrumented.
Any prediction as to the limits of what one can do is disproved, rather rapidly in the future. I would have thought if it's not against the laws of physics to do it, it can be done, and unless it's too expensive, it will be done. I don't see why not. People like Freeman Dyson have speculated very seriously along those lines. Yes, I think it's maybe not for a couple of centuries, I don't know, but I don't see why not.
A conversation with Dyson that made me think about some
yes.
question.
Yes.
able to do experiments so you can go farther and farther with your fantasy and make speculations.
One paper, if you assume it was a major priority for some sufficiently wealthy organization or country, you can use the fuel. And you can have a big ponderous microwave beam in orbit, which is accelerating a few tens of grams of instruments with an umbrella behind it. And on paper, highly optimistic assumptions show that if some technologically developed country considered it a major national priority,
Yes.
it could be done in a few decades. And can be done means that once you develop this thing, you could get to interesting astronomical objects in travel times of 10 years or so.
Oh, I see.
10 years.
Well, another thing I should mention is that Dyson is convinced that within just a few light years of us, there are bound to be interesting objects that haven't been discovered yet.
Uh-huh. Why does he think that?
Well, because many astronomical objects are undetectable. For instance, theory says that neutron stars should be almost as numerous as ordinary stars, but only a few hundred are observed. Most of them are too dim.
Yes.
So there should be a lot of dim neutron stars and black holes in our neighborhood.
Space stations find similar things even though they are not very far off. Just because they have no constraints on the atmosphere, the dimness will be reduced.
Well, I don't think Space Telescope would be able to see the objects that Ed has just spoken about. It will be able to see fainter objects because there is not the scattering from the atmosphere, and it will have much better angular resolution and much wider wavelength coverage. So it will be tremendously important for astronomy.
What
But it
would the
wouldn't.
scale of luminosity go up to?
Well, it would be able to see galaxies something like, this is not a very accurate answer, something like 10 or 100 times fainter than we're now normally used to seeing.
Yes.
But to see objects of the kind we were just speaking of, I don't nobody particularly expects Space Telescope to be able to do that. But it will still change astronomy, I think, with its new powers, rather like when Galileo essentially used the first telescope.
That's a tremendous change.
So that's
a tremendous
That's why the Americans are willing to spend so much money on it, because it will still change astronomy very greatly, but not to the extent we're now discussing. Well, actually, with the European support, the Europeans are involved in the Space Telescope by building an instrument for it. We buy our way onto Space Telescope, and we get 15% of the observing time.
Yes.
By spending, I suppose, 15% or whatever the fraction is of the cost. And we do it by building a particular detector.
What amount of money is involved? Do you have any idea?
Gosh, I don't remember now. This number keeps changing. I don't want to say a number that's wrong. But when we say who are the Americans, well, NASA, American government through NASA.
No, but is it a $1 billion project or a $500 million or less?
It's not too far off. From
not too far off, I should think. Yes. So for tens or hundreds of millions, we build this particular detector. We, the Europeans.
Yes.
And buy our way onto the instrument. So we get 15% of time on an instrument we could never possibly built ourselves as Europeans.
Yes.
So that's
with President Reagan putting an 8% on taxes and for the sake of SDI, maybe the next administration can change the same amount of money onto space science. Shouldn't one vote? No, really. Suppose he gets it through the Congress. Next administration may have an easier job, just changing the objectives.
Yeah, this could be a resolution.
Just changing the objectives.
I wish I could believe that was likely to happen. Well, unfortunately, I don't know if the first part will happen, but the second part, unfortunately, if it gets through as Star Wars, to hope that it will be turned into space science seems a little bit optimistic.
Right.
To me, it seems like a natural concern that once Star Wars gets rolling, there will come to be a lobby for it of contractors and people working for Star Wars who depend on it for their livelihood. And there will come to be a Star Wars lobby that has nothing to do with any alleged virtues or, for that matter, any faults of Star Wars as a defense system. Why did you say before that cosmic strings are no longer alive for galaxy formation?
No, Abdus said it, not me.
What did I say?
I didn't
What's
say
your
that.
opinion about it?
Well, it's not something I've worked on. I think it's still taken seriously by a small number of serious people like Tom Kibble, who's just at the moment writing new papers on the subject.
Yes.
But it was you said, Abdus, that cosmic strings for making galaxies are now dead. I let it pass, but actually I didn't quite know
what I meant. Dead in the sense of doing anything with them experimentally. Dead in the sense that they've done their job, and that's the end of it.
Well,
the galaxies have been made, and now you will not know whether they were at the bottom of the business or not, and what more could you do with them? They've done their job.
Well, the ones that created
no more galaxies.
No
more galaxy creation.
Oh, there are predictions, actually. For instance, if you just say that galaxies were made by nucleation around cosmic strings,
yes.
It turns out that those cosmic strings, in the process of disappearing, would have created a detectable amount of gravitational radiation.
Would have.
Yes. So while the theory can't be proved, it can be disproved by not finding the gravitational radiation.
I see. Well, that's good then.
But there's another example. According to Kibble's latest work,
yes.
You can calculate from the string theory of galaxy formation what you'd expect to get for the correlation function of the galaxy distribution. That is, if you know there's a galaxy here, what greater probability than average is that there's another galaxy nearby. This is a correlation function which is known observationally very well.
Yes.
The main architect of that work is a colleague of Ed's at Princeton, Jim Peebles.
Oh, yes.
So observationally, this correlation function is known well, and according to Kibble, you get very well that function out of the string theory.
I see.
Without any adjustable parameters designed to get it.
But
that made the
then, what Ed
galaxies.
is saying now, you would also expect some gravitational radiation to be around.
Yes, I think so, Hans.
But
The chances of detecting it, well, observations of relic gravitational radiation are likely to improve significantly in the next 10 years. And there's a reasonable chance that this string picture can be disproved or supported in a reasonable time.
Will provide the 21st century equivalent of a new detecting device for particle physics or for other phenomena like the ones we are talking about.
Well, it's a timely moment you ask me this, Abdus, because next week I'm going to England for a conference on gravitational wave detectors.
Yes.
The British group based on Glasgow is attempting to raise money from the Science Research Council for an ambitious detector, and they're bringing the leading people from California and Italy, I suppose, and Germany.
Yes.
And the hope is that in the next 10 years, gravitational wave detectors will become sufficiently sensitive, not perhaps to detect these waves we were now speaking of, but to detect supernova, stars collapsing to make supernovae
Yes.
in the Virgo cluster of galaxies.
Yes.
There's about one event a month, I suppose.
Uh-huh.
And these can be picked up with detectors, not today,
Yes.
but the sensitivity required is programmed to be achieved in the next 10 years.
With which they will increase their sensitivity.
Well, over the
today.
present, I don't know I'll know the numbers better next week, but something like 100 times better than they can do today, I suppose. But the technology seems to be online to do that, using laser methods and so forth. It's fantastic technique. It's something like getting a ton of material in the form of a bar and detecting a change in the length of that by something like 1/10,000th of the radius of an electron.
Oh.
And they aim to detect these small length changes. That, in effect, is what the measurement involves. And that's what's required to see the gravitational waves from a supernova event in Virgo. Now, these particular things that Ed was talking about might occur at different frequencies and would need different techniques.
There are lower frequencies.
Yes.
And the interesting possibility of detecting them comes from their influence on the timing residuals of pulsar observations.
Right, yes.
I mean, for the explanation of clusters of galaxies and supercluster, this is not, I mean, a good explanation now with fractal methods. With fractal, I mean...
What is fractal methods?
With Gauss and other, I mean, this fractal, Mandelbrot, I mean, methods. I mean, I heard this, I mean, from Ruffini. Ruffini, I think, is working on that. And there are people also in Copenhagen talking about the possibility of explaining the distribution of cluster of galaxies in the absence of superclusters.
But is this a matter of just mapping the distribution with some mathematical technique, or the physical explanation of how these objects form?
No, this is more
it's more description of their distribution.
Yeah, that's right, yes.
Mm-hmm.
Well, I'm sure more sophisticated methods will be used to specify the distribution you're trying to explain, but I must admit, as a physicist, my main interest is what physical mechanisms actually occurred, and do you need exotic things like strings, or can you use more old-fashioned ideas? Although other modern ideas for making galaxies are just as exotic as strings, but don't happen to involve strings. Things like quantum fluctuations in the very, very early universe near the Big Bang, involving the so-called inflation process, is a very popular way now of making the initial disturbances that eventually evolved into galaxies. So the link between very large things like galaxies and the sort of things in microphysics we started out talking about with Ed, this is one of the great developments in recent years, that this discussion is possible.
But coming back nearer home, I mean, don't you find, Dennis, you and I are old people, that things have changed so much in our lifetime?
They sure have.
Haven't
I don't know which change you have in mind now. There have even been so many changes, but...
Well, for me, certainly the biggest changes, when I started life, things were chaos. And now there is some sort of semblance of order, and there's a chaos of a different kind altogether. I mean, there's a chaos which is ordered chaos, if you like finding what the string theories are saying and so on. There's a different, there's an objective insight. There was none whatsoever when I started. Now what I wanted to ask you was, is the same thing happened in your subject?
I don't know which change you have in mind now. There have even been so many changes, but...
Atom and hydrogen filling the universe was known. Fred Hoyle existed.
Well, Fred Hoyle existed, all right. Yes, he was.
Yes, he was the pioneer of all those things.
Well, when I started research, none of the revolution in modern astrophysics had occurred. I'm not saying there was a connection between the two things.
You had a
Cosmological
did that
theory.
give you
by
as a
then.
problem?
And I started research
Helium.
around 1949
Yes.
under Paul Dirac, in fact, whom
Paul Dirac, you are one of the students of Dirac?
yes, whom
Good
we are
heavens.
remembering at these times
Good
very
heavens,
much.
good heavens. What did you do with him?
Well, you may well ask. I started research in a different part of physics, and in the middle I changed to relativity in Cambridge.
Yes.
And so they hurriedly gave me Dirac as a supervisor to make up for this rather strange way of life.
In 49, I started research in 49 too.
Well, I got my PhD in 53, and I changed in about 51. Dirac became my supervisor. But since I'd worked out my cosmological
did that
theory
give you
by
as a
then-
problem? What were you
No,
doing?
no, I had worked. You see, I'd worked on a problem and told the authorities that I'd changed from statistical mechanics, and they
Oh,
got
I
a big
see.
cross.
Ah,
And they said, well, we can't keep you with your old supervisor.
Yes.
So, and there weren't many people in relativity in Cambridge at that time, so they gave me Dirac. But I'd already worked out my theory, you see. It was no fault of his. He didn't neglect me or anything. He had no opportunity to look after me, but officially he was my supervisor.
I
And I saw him a few times and got
and
to
you were
know
working
him.
on the famous Sciama, this sort of
Some old nonsense about Marx principle.
Kibble and... Oh, no.
No, it wasn't the stuff on torsion. It was before that.
Oh, it was
It
before
was
that.
things to do with Marx principle.
I see. Mm.
So anyway, that's but the modern
How
era.
often did you see Dirac altogether?
Oh, 4 or 5 times, I suppose.
I see.
You know my favourite Dirac story. I go up to him once and I say, Professor Dirac, I've just thought of a way of relating the formation of stars to cosmological things. You see, not galaxies, stars. Shall I tell you about it?
Yes.
And he said, no. So I loved that.
And then what happened? You
So I went away, and 2 days later I realised it was absolute rubbish. But I'm not answering your question. The thing is, the New Deal in astrophysics really began in 1952
Yes.
with the idea that the radio noise from the galaxy was due to synchrotron radiation, that is, relativistic electrons moving in the interstellar
Why do you
magnetic
call it a
field.
revolution?
Well, because once we understood that,
Yes.
we could understand that one could observe radio sources radiating in the same way from objects much more distant than could be seen by optical telescopes. So when people like Martin Ryle started mapping out the radio sources,
Yes.
many of them, you see, that later some were found to be quasars and so on, but at the time it was clear that one could see objects in the radio that would be too
I
far
see,
away
Martin
to be
Ryle
visible
and so
optically.
on,
So you could survey the universe out to much greater distances than before.
So you would call the revolution as the radio sources
So
mapping and
beginning
so
to
on.
understand radio sources was the beginning, and then quasars emerged out of
Yes,
that.
so
And
quasars are still not understood.
no, but it's an example of the revolution, I mean.
No, but that's
Oh, we now understand them, I think.
in what way?
Well, that it's, we work on it here very strongly, in fact, that it's
Black holes.
accretion disk around black holes. It's not proved, but it's very likely to be correct.
Well, that's likely, but anyway, that's not going to be a revolution in thinking. Like what exists. in
Well,
the
you
radio
say
sources.
that now, but black holes, not only black hole, I can remember when even a neutron star was considered not a respectful thing.
Well, generally, I think that we are practically at the end, no? Isn't it? And so it is very hot here, and I think that we have to thank our all of you to have been so kind to make this show. However, it was interesting. Well, it was a show.
I meant every word of it.
Not a show. Not a show at all.
I'm sorry.
We were doing
No, it was very
serious,
amusing.
serious
I
discussion.
know.
Good
It
heavens.
was amusing. Only it
Yeah,
was very
it's
hard.
an
I don't want to
insult to
profit
call
of
it a
your
show.
patience.
Yes.